For the next part of our unit, we're going to be changing gears from talking about what thermodynamics is to where the data from thermodynamics comes from. And all data, no matter how you do it, ultimately comes from this process today, a process known as calorimetry. Let's start with a quick list of the learning objectives for this video. We'll begin with a review of heat systems yet again. I know this is a topic we've talked about a couple times now, but in this particular scenario, when dealing with calorimetry, heat systems are particularly important. So we need to make sure that this idea is fresh in your mind. We'll then get into the actual heart of the matter. First of all, what is a calorimeter and how does it work will be the major concepts of the day. And then last but not least, we'll focus on the mathematics that goes along with this. The great news is you've already seen the equation we're going to be dealing with. Q is equal to mc delta T. The question is how can we use it in conjunction with the data that comes from machines like this in order to determine things like delta H and values for the specific heat, or C, which is what calorimetry is really all about. So as I said, we'll begin with a quick reminder of what heat systems are all about. It's all about defining a separation between the system, what we're focusing on, and what's surrounding that system. In endothermic reactions, heat is moving from the surroundings to the system. We often see this as a temperature change going down in the surroundings. And in exothermic reaction, we see heat going out of the system, which means we expect to see a temperature change increasing on the outside. We generally can't feel what's happening inside the system. We can feel what's happening in the surroundings, and that's why I focused on these statements right here. Again, keep this fresh in your mind. This will be the basis for how calorimetry works. So let's move on to the main topic here then. What is a calorimeter? Well, basically it's a device that allows us to measure the amount of heat that goes into or out of some sort of process. Calorimeters come in a lot of different sizes, shapes, and flavors, which is why I'm being a little bit vague here when I say the word process. We have calorimeters designed to measure things like chemical changes or chemical properties, for example, the delta H of a reaction. We also have other calorimeters that are focusing on more physical properties. These guys you'll talk about more later in the chapter. The heat of vaporization, the heat of fusion, and the heat of solution are the energies that occur during physical changes. Vaporization, for example, is the energy required to get something to boil per mole. We've already seen so far this year the concept of specific heat, C, and all of these can be measured with a calorimeter. What a calorimeter does then is it doesn't measure heat, and we talked about that's something we can really do, but what instead it measures is temperature changes in a tank of water that's surrounding the actual process itself. This tank of water ends up behaving as the surroundings in our reaction, and depending on how much the temperature changes, we can see what happens in the reaction itself. We then take the equation Q equals mc delta T and we relate to the temperature change, which is this factor right here, which correlates to a value of Q. If the water changes a certain temperature, that corresponds to a certain value of Q, and that value of Q must be the same as the energy or heat that came into or out of the reaction due to conservation of energy. What we'll assume for the rest of the chapter as our last piece here is that Q and delta H are the same exact thing. This is not entirely true, but that's only in all cases. There are certainly times where it is the scenario, and we're going to focus on those times. There are other times where delta H encompasses more than just heat energy, and those concepts are a little more complicated, and those would be for thermodynamic topics later on down the road. So here's some quick diagrams of what a calorimeter can look like. It can be as simple as what we call here a styrofoam cup calorimeter. We've got an outer styrofoam cup that's filled with, well, actually, we got 2 layers of styrofoam cup just for extra insulation. We do some sort of reaction inside. This tank here would be filled up with water, and we can measure the temperature change in that water using a thermometer. This is a more complex version, but it's exactly the same device. We've got a place to put a thermometer right here to measure temperature changes in the water. This connects to a device that allows you to stir the contents to make sure the heat is evenly distributed. And in this case, this is a bomb calorimeter. We can actually use electrical contacts here to spark a chemical reaction to happen and then measure what that so if this is the chemical reaction right down here, we can measure then how much energy the chemical reaction releases or absorbs into the water. All of this can be obviously scaled up, and we have a much more lab-grade version here. This would be a device that does automated calorimetry measurements for measuring the delta H reaction in more of a high-throughput kind of environment. The scientist could put a sample in here, set things up on this control panel, and the machine will do all the work for you, spitting out an answer at the end. So let's take a little bit more of a closer look on an actual calorimeter. This is an example again of that bomb calorimeter I showed you before, but I'd like you to show you what all the components are here. And what this bomb calorimeter is designed to do is it specifically measures the delta H of combustion reactions. So we start with a reaction vessel, which is what this guy is right down here, and labeling the parts of this isn't a bad idea. Here's where our chemical reaction is going to run. Now since it's combustion, that reaction is going to be exothermic, and it's going to release heat energy into its surroundings. In this case, the surroundings is this tank of water. We will use a stirrer to make sure that the water moves around so all the water is the same temperature, and then we're going to use a thermometer to measure the temperature of that water. As the reaction gives off energy, the delta H of reaction, which is what we're trying to measure, will determine how much heat energy is given off. That delta H of reaction we can represent as the letter Q because we said the two of those are same, and it'll be the amount of energy that comes out of the reaction should be exactly the same as the amount of energy that goes into the water because of conservation of energy. Assuming no energy is lost in this process, the only thing that's causing the water to change temperature is the reaction that's happening inside. So the amount of heat energy here is both. We do end up adding in an extra negative sign here because they're moving in opposite directions. Energy is moving out of the reaction and into the water. What this then allows us to say then is, well, we already know that the Q of the water is equal to the mass of the water times the specific heat of the water times the change in temperature of the water. These are values that we can measure. Water specific heat we know is 4.184, mass we can determine, and delta T is something we measure with the thermometer itself. That will get us the energy that went into the water, which we already know corresponds to the energy that must have come out of the reaction, which eventually leads us to a value of delta H. So through some simple measurements of temperature and some simple calculations using our equation here, we can take some values like the mass, specific heat, and change in temperature in a water and use that to determine how much heat energy must have come out of the reaction itself. So now that you've kind of seen the basic idea of how things work and some of the preliminary ideas of the mathematics, let's see if we can't get a little bit more specific and talk about the calculations. There's always two parts to a calorimeter system: the reaction vessel, which is our system, and the water reservoir surrounding it, which is our surroundings. The assumption that we make, and this is key here, is that no heat escapes. This is never actually true, but higher and higher grade calorimeters get closer and closer to this, but this is always going to be a source of error for us in any type of calorimetry measurement we make. We always have a little bit of heat escaping. The statement we already made in the previous slide is that the energy that goes into or out of the water must be exactly the same quantity of the energy that came in or out of the process, but we add in this extra negative sign to denote that the direction is different in both cases. And then we can take usually the equation for water and break it down into its components and get them down to variables that we can actually measure. Again, mass of the water sample, the specific heat of the water sample, which is always 4.184, and then the delta T, which we measure with a thermometer. This can be used for both chemical and physical processes that we talked about earlier. We're going to go through some examples in a second showing you how it works in each case. So here's the example of talking about calculations for physical properties. These calculations are typically for measuring the specific heat of your sample. Again, we go back to our main premise for calorimetry, and this is really what calorimetry hinges around, is that the amount of heat that goes into the water must be the same as the amount of heat that came out of the substance, or vice versa. We can replace both Q statements in this scenario with the MC delta T equation. We can take the mass of the water times the specific heat of the water times the delta T in the water, and that must be equal to the mass of the substance we're dealing with times the specific heat of the substance we're dealing with, and the delta T of the substance. Mass of the water we can measure, determining how much water we put in. Specific heat is always given to us. A thermometer will measure delta T of the water here. The mass of the substance is something easy to know, and the delta T of the substance is not always obvious, but it can be figured out based on the other data we collected, leaving us with the ability to then calculate or solve for this missing variable here. A great example of this is measuring the specific heat of the metal. You plop the piece of metal that's hot into a cold tank of water. You measure how much water temperature the water goes up. You determine the initial and final temperatures of the piece of metal, and then you plug all of that data in here and solve for your value of C. We can also do this process for measuring delta H values in more chemical type scenarios. Same process again, where we make our main assumption here, the fact that the energy going into or out of the water must be the same quantity of energy that came into or out of the reaction. And then we can talk about what we did earlier. Well, the heat of the reaction then must be equal to the mass of the water, which we can measure, the specific heat of the water, which again we're always given, and the delta T of the water, which comes from the thermometer. We can calculate this, and then as we talked about, this value ultimately leads us to the value of the delta H for our particular reaction itself. So again, we can do the same process with the same mathematics and calculate delta H as opposed to just calculating specific heat. So that's pretty much it. Hopefully what you're seeing here is, again, we have a scenario with some pretty simple mathematics. It's more of how to apply and use that mathematics that can make this process a little bit trickier. You should be able to explain what calorimetry is used for, again, primarily for measuring values of delta H or measuring specific heat of substances. You should be able to describe the parts and the function of a calorimeter. I think if you can do this, the rest of the stuff becomes very simple because you understand what a calorimeter is, how it works, and then the data that we collect obviously ties back to the mathematics. I think it makes things a little clearer to understand. And last but not least, you should be able to use the idea of conservation of heat energy in order to practice this. And that's really the idea of saying that the Q of whatever your process is must be equal to the Q of the water that it reacts in. And as long as conservation is in play here, our calorimeter allows us to plug in data to the equation, Q equals MC delta T, and calculate what we're looking for. And again, calculating delta H, calculating specific heat, and then hypothetically, you could calculate any other variable, but practically speaking, why wouldn't you just figure out the mass by putting things on a balance? As always, we'll be practicing these pretty significantly in class in both forms, and we're also going to be doing some lab work that's going to allow you to put this into actual practice with some real calorimeters.